Hello, welcome to the Carl Cymru session for Year 12 AS Chemistry. And today I'm going to be covering 2.3, the wider impact of chemistry. My name is Mr. Black and I teach at Penglade School in Aberystwyth. Okay, so if we look at the syllabus and the wider impact 2.3, we can see here that actually there's not a great deal that is mentioned, but it actually covers lots and lots of chemistry that you studied. You just have to know where it applies into those statements. So we'll go over and sort of see various aspects of the course being applied to these 2 points. A really good place to go to, of course, in terms of looking at the syllabus is look at the knowledge organizer, because the knowledge organizer kind of gives you a bit more detail about what areas specifically they want you to think about when you think about the wider impact of chemistry. I guess there you can see here the biggest impact of chemistry is thinking about the impact it has on the environment and people. So we're going to very much develop those things today. So I'm going to focus in first of all on what we call green chemistry, which I guess is the impact it has on people and the environment. And you'll see here on the next slide that oh, actually no, you won't see. I'm going to talk to you first about this word sustainable. So when we think of green chemistry, we think about chemistry that processes that are sustainable. And what does this word sustainable mean? Well, sustainable is what we call the 3 pillars. So, for example, your 3 pillars are social, environmental, and economic. So we need to consider, like, for example, people's jobs, the sort of environment they're working in. We need to consider the environment, so how polluting is the stuff we're making. We need to consider how, I don't know, how we obtain the materials to produce the final product. We need to think about how we dispose of the final product. And then also we need to think about, are there going to be resources for future generations as well? So if something's going to run out, then it's not sustainable. It's not there for future generations. To be sustainable, you need all 3 of those aspects. The economic one is basically, if something is sustainable, i.e. meeting social and environmental aspects, but no one can afford to buy the product, and there's a cheaper thing that isn't sustainable, your product's not sustainable. Your product has to be affordable as well. Like I say, we're focusing on the chemistry aspects of sustainability. And when I think about those, I think of the 12 principles of green chemistry. And you can see here, I've highlighted the aspects that I think are particularly relevant to your course. And the first one I started with is the pollution prevention. Okay, so we look at pollution prevention. Okay. We're going to start off with this guy here. This is Newcomen, and the reason that I've started with him is, at least know his name, but he's really the father of the Industrial Revolution. He developed the first steam engine. It's actually a water pump, and it was there to pump water out of mines so that they could mine deeper. And with the advent of the steam engine, we then kind of start to apply it in various different aspects. We ended up with the Industrial Revolution, and you can see here that the Industrial Revolution, I guess chemistry capitalists rather than chemists, are affecting the environment. I mean, they're applying the principles of chemistry here. They're certainly not considering what impact it's having on the environment, and certainly not on the people who live very close to these factories, the workforce. So since the Industrial Revolution, we've been polluting our atmosphere. Okay, and we still are, just not as badly. Okay, and so significant improvements in what we're doing. I'm going to focus in on global warming, but you can think about also acid rain, because when we're burning fuels, especially fossil fuels, we're burning sulfur. You're burning sulfur, producing acidic gas like sulfur dioxide, and that will go into the atmosphere to form sulfuric acid, acid rain, and then you get your nitrogen dioxides forming as well. From the heat of the process, and these form your nitric acid. But as I say, we'll focus in on global warming. So burning fossil fuels, as you hopefully know, produces carbon dioxide gas. We should be able to write the equation for the complete combustion of a fuel, especially a hydrocarbon and an alcohol. And you can see here that the carbon dioxide gas, being a greenhouse gas, traps heat. Okay, so some of the heat from the earth warming from sunlight escapes to space, but some of it gets trapped by these greenhouse gases. The more of those greenhouse gases in the atmosphere, the more heat we trap. Okay, and then we get this unnatural rise in Earth's average global temperature. Don't forget, by the way, the greenhouse effect is vital to life on this planet. We need a greenhouse effect. Without it, the temperature on the planet would be about -18 average, and you wouldn't be able to sustain life. So greenhouse effect is good. Too much greenhouse gas, not good. So one of the things when we're thinking about an industrial process, chemical process, is where we get the energy from for that process. And we've got these more sustainable methods, perhaps, than fossil fuels, although always consider how sustainable these things are. So, for example, hydroelectric, yeah, no polluting gases. However, lots of concrete, lots of greenhouse gases in their production. Quickly paid off. But then you've got to flood valleys, you're destroying habitats, you're destroying people's homes, even people's culture. Perhaps think of Covered Wearing. I hope I pronounced that correctly. But, we flooded valleys for drinking water, to be fair. But the impact on the culture can be huge. The impact on the environment can be massive. Solar, yeah, great. But you've got to produce those solar panels. Some really nasty chemistry involved in that. Quite a lot of pollution. So you could call it almost greenwashing, but definitely better in terms of greenhouse emissions. I'm going to focus on the biofuels, though. Yeah, biofuels definitely have advantages, but as you'll see, we've also got some issues you need to consider. Okay, so yeah, the biofuels brings me on to another principle of green chemistry, which is energy and feedstock. Okay, and it's on your syllabus, on your knowledge organizer, it will say, well, we need to use plant-based compounds wherever possible. Okay, so we'll discuss where we do that and perhaps the implications of that. So here's a potential feedstock or fuel for us. Maybe you recognise this plant. This is palm oil. And hopefully you're aware of the issues regarding palm oil. They are massive. Palm oil, incredibly useful. Okay, it's a renewable feedstock. Plant grows, you harvest the plant, you plant more of that plant, and you grow more stuff. Okay, so it's never going to run out. So yeah, that's why it's a renewable feedstock. And you can see palm oil, obviously it's a massive use in food, but also it's got some industrial chemistry in here. We've got it used as a biofuel, a bit like diesel. And also we've got it in terms of, making cosmetics, detergents. You'll find palm oil in lots of things, not just food. Okay, so yeah, renewable feedstock, fantastic. Let's grow lots of palm oil. And of course, when I think of biofuels, I particularly think of ethanol, bioethanol, again, a biofuel. Ethanol, as you hopefully know, comes from the fermentation of sugars, the anaerobic respiration of yeast, known as fermentation. This is sugarcane. I grow lots of this in Brazil and those sort of climates. Okay, and that then can be turned into alcohol. So there's your glucose from the sugarcane. Yeast, using its enzyme, zymase, carries out respiration, anaerobic, you'll notice there's no oxygen as a reactant, to form our ethanol. And that ethanol can then be distilled off and then put into our fuel. And you can see if you go to a petrol station, you'll see on petrol, predominantly now, you'll see E10. Sometimes you'll see E5. We were mainly E5 up until recently, but government legislation now has pushed us towards the E10 fuels. The E, hopefully understand, represents for ethanol, and the 5 and the 10 represents the percentage that they make up of the fuel. So hopefully the government thinking here is that by putting in these biofuels, we're having less impact on carbon dioxide emissions. Okay? Now we just need to consider that. So why would burning ethanol rather than petrol reduce carbon dioxide emissions? Well, if you look here, actually, when we burn ethanol, and you should be able to write that as a balanced equation, by the way, combustion of any alcohol. But when you burn ethanol, it does produce carbon dioxide, which is a greenhouse gas. So a really good word to use, we talk about biofuels, okay, is this word carbon neutral. And the reason we have this word carbon neutral is that, yes, burning the fuel does produce carbon dioxide. However, carbon dioxide was taken in when the fuel was growing. So you can see here I've written the equation for photosynthesis. So yes, carbon dioxide is released when you burn the fuel, but carbon dioxide was taken in when the fuel was being produced. So yeah, carbon neutral. So it's quite an important term to use. Make sure you can discuss it. So yeah, great for the environment, fantastic biofuels, biodiesel from your palm oil, bioethanol from sugarcane. But as you saw earlier, this slide came up, which is really quite a tragic slide. Where are you going to grow your palm oil? Indonesia is particularly well known for its palm oil, and this would have been a rainforest. This would have been the habitat of this orangutan here. You can see it's actually trying to protect its habitat from it being bulldozed and cleared to make room for our palm oil. So negative impact of biofuels, biofeedstocks. Okay, so that's one of the issues, are biofuels. Also, if you're going palm oil, well, there's only so much palm oil you can eat. This could have been used for agriculture. So this could have been grown for food for local population. Obviously, if there's less land for growing your food, then prices are going to go up because there'll be less food available. And there's actually been riots across, various nations, developing nations, where they're a bit fed up with the fact that their food prices are going up because they're producing fuels for Western economies. And then there's another issue as well. We've got this thing called monoculture. Okay, so where you've been growing your palm oil, your sugar cane, or whatever food crop you're growing, you're taking out a whole diverse ecosystem and you're replacing it with one plant that might be able to support one or two species. But obviously, great biodiversity in your producers is much better. There's another issue as well with these biofuels, and that's we need to use fertilizers to grow them, okay, because we're taking this soil or these nutrients. Fertilizers in their production, they produce carbon dioxide in huge amounts. The Haber process is particularly known for producing carbon dioxide. Remember, Haber process produces ammonia. Ammonia is in fertilizers, okay? And also I've got here, with using fertilizers as well. Those fertilizers can wash into water sources and they can produce issues such as eutrophication. So yeah, you've got some major issues with your biofuels and your biofeedstocks. Okay, so moving on. Just very quickly, you'll see there one of the things mentioned in our green chemistry and our wide impact is this idea of atom economy. Atom economy is just a process by which you can work out the amount of waste and the efficient use of a resource. Okay, so there's a little kind of statement about atom economy for you to read. Okay, and why we need a high atom economy. So high atom economy is linked with high sustainability. You need to be careful with that statement. I'll just discuss why in a second. So you need to know how to calculate atom economy. You can see there, it's basically the MR of whatever you're trying to make divided by the total MR of all your products, and then you multiply it by 100. 100% atom economy is fantastic for sustainability, but might not be fantastic in other aspects. And we'll perhaps discuss in a second why. So there you go, quick question for you to do. Pause the video, see if you can work out the atom economy for obviously making aluminium. Okay, so I'm going to just go through that with you now. So obviously the aluminiums are used for product. Okay. So our atom economy is 27, which is the AR, relative atomic mass of the aluminium, multiplied it by 4, because we're not making 1 mole, we're actually making 4 moles, and then divided by the 102, which is the MR actually of the reactant, and I've multiplied, that's 102 is the MR aluminium oxide, molar mass, aluminium oxide, multiplied by 2 because we're using 2 moles. So you not only take into account the MR or AR values, we take in the stoichiometry as well. Okay. There's a question from a paper. Are tetriles the useful products? Okay. And it says, why is it not 100%? And so, well, 1 mark, what do I say? Well, it's quite a simple answer. Go to the mark scheme. It's basically there are other products formed. If you had 100% atom economy, you'd only form one thing. And you can see here, we're not introducing tetral, producing some methanol and some water as well. Hence the not 100% atom economy. There we go. And that's how you'd calculate your atom economy for that reaction. There's the MR of the tetriol. There's only one well formed. And here I've used all the React products this time. So there's the MR tetriol, there's the MR of the methanol, and there's the MR of the water multiplied by 3. For some reason, people always forget how to do atom economy, so make sure you are familiar with it. It's quite often asked in exams. As I say, the higher the atom economy, potentially better than sustainability. But what you need to consider is, well, okay, how much energy was used to produce the product? Where did the raw materials come from? Did they have to be mined? Did they cause pollution in obtaining them? Are those materials renewable materials, or there's a limited amount of them and finite, non-renewable? Yeah, you need to consider more than atom economy to talk about green chemistry. It's just one thing that we can consider. Question here. I'm not going to do this question. There is actually a link that will be on the PowerPoint for you to follow. It's actually a really difficult question. It takes a little bit of thinking, a bit of a rearrangement basically, but I've got the answer there for you. So definitely worthwhile having a go at, because it's something that the WJC might ask one year. I've never seen them ask this, but I came across this once and I thought, wow, that's a good question. It's actually from a GCSE paper. So click on the link and yeah, follow through the working through that. It's quite a good one. So also one of the principles of green chemistry then are safer solvents. So I'm going to bring you into some that you have studied, and these are your CFCs, okay, which stands for chlorofluorocarbons. Okay. This is what you can buy now. Okay, if you want a solvent, well, actually, no, this is what you can buy now. This is what you can't buy now. This is what people would like to buy. In fact, I used to sell these sort of chemicals, and I mean, this CFC solvent. Oh, this is CFC free. Yeah, people wanted solvents with CFC in. The CFC solvents are very, very good at doing their job, which is like dissolving greases, cleaning things, improving electrical contacts. You can't buy CFC solvent now. You can only buy this stuff, which is CFC free. We've taken CFCs out of solvents, and there's a reason for that, and a good reason for that. So this is a CFC, okay? And we can see here, it's a carbon, fluorine, and chlorine molecule, okay? So what's the issue with the CFC? Well, it's to do with the fact that the chlorine in our CFC, see here, they can go under bond fission. And I'm just going to pause again. I'm going to ask you a question. What kind of bond fission can you see happening here? And hopefully you've said this is homolytic bond fission, where both bond pair electrons go to each of the atoms to produce free radicals. And it's these free radicals that are produced that create an issue. So you can see here this covalent bond with 2 electrons in, 1 electron's gone to the carbon, the other electron's gone to the chlorine, which hence we're saying we're using the term homolytic bond fission. That's generated this free radical. This free radical then reacts, goes into our atmosphere, goes into the upper atmosphere, and it reacts with ozone. And it destroys ozone. Okay? It turns ozone basically into oxygen. And the issue with that is that ozone is basically very good at protecting us from harmful UV radiation. Okay, and you see here there's an image of what's called the ozone hole. So the blue, this is Antarctica. I can't quite see on the map. You can see here we've got this big blue hole over the Antarctica, and yeah, that means they're not getting as much UV protection. And hopefully, you know that UV can go on to cause things like skin cancers. So we see here is an Australian cricketer, because Australia kind of is in that region where we have this whole ozone layer. They're very protective in terms of exposing themselves to UV light. So they put a zinc block on here to stop, you know, getting skin cancer of the nose. Australians quite often don't wear caps like this. They'll tend to have caps that protect the ears as well, stop sunlight getting on them. And that's why, yeah, CFCs were banned, okay? Because they, you know, the carbon-chlorine bond breaks, bonds into free radicals, and then we have our issue of ozone depletion. So since they've been banned, we've got a heel now in the ozone, and long may that continue. Okay, so hopefully by some point we won't have that problem. So what is it about the CFCs? Well, it's to do with the bond enthalpies. Okay, So if you look at the carbon to chlorine bond, it's got a lower bond enthalpy of 346 compared to a carbon fluorine bond of 467. So this bond breaks in ultraviolet light in the upper atmosphere. Okay, if the bond's stronger, i.e. replace the carbon chlorine bond with just carbon fluorine bonds, then we won't get this homolytic bond fission and we don't form the free radicals. Okay, so this is what's in your CS3, that drum I showed you earlier, the CFC-free solvent. This is a CF solvent. There's no chlorine in this. There's nothing here that's going to undergo this homolytic bond fission. You're not going to form free radicals. The only problem is it's not quite as good solvent as the CFCs. Okay? But hey, at least we don't have a whole new ozone layer. Okay, so those are gone and replaced by these. You can see there little just a little mechanism. You should be familiar with homolytic bond fission. Results in the formation of free radicals. Both bond pair electrons, well, one of each bond pair electron goes to each atom. Trying to find a better definition than I've just given you there. And then finally, that brings me on to catalysts. Okay, catalysts are incredibly important in the industrial processes. So what's a catalyst? Well, you obviously need to know what catalyst is. This comes on from your, I can't remember which module it is. I think is it 2.3? I don't know. It's one of your modules in Unit 2 anyway. Rates of reaction. I think it's 2.2. Basically, what's a catalyst? Well, make sure you learn that. They're substances at speed of chemical reaction, event only going to change by, and this is the important thing, providing an alternative route with a lower activation energy. Okay, so there's our energy profile diagram. We can see the red line is a catalyst, catalyzed reaction. This is a different route with lower activation energy. This means more of our collisions are going to be successful. Okay, and hopefully you're familiar with this curve. This is called our Boltzmann curve, something that you've got to be able to strong exam. And we can see there with a catalyst, we have a lower activation energy. And what that means is then we have more particles in the shaded region past the activation energy. Okay, so the greater area under the curve. And this shows we've got more particles with sufficient energy to react. What does that mean then? Well, that means we can do reactions at lower temperatures. So the obvious thing there is that we're saving energy. In terms of the environment though, because this is wide impact, if we're saving energy, we're using less greenhouse, fossil fuels perhaps. There's less demand on fossil fuels, and therefore we're going to produce less greenhouse gases. Okay, so that's great for the environment. Yeah, and I just threw this one in as well because I thought it was particularly relevant for us. Catalysts as well are massively important for reversible processes. And I just want to have a look at this graph here. And I want to tell me what you know about the forward reaction from this graph. It's always worth a little think about. So I will pause for a moment. I'll let you pause. So what does it tell me about the forward reaction? Well, let's first of all explore what's happening with temperature. If I increase temperature, okay, I can see my yields going down. Okay, my yield's going down. I'm not favouring my forward reaction. So that tells me that my forward reaction must be exothermic. And I'll explain why. Le Chatelier says if you increase temperature, you favour the endothermic reaction. Okay, so if I'm increasing temperature and my reaction's going backwards, yeah, because my yield's going down, my backwards reaction must be endothermic, which means my forward reaction must be exothermic. So catalysts are particularly important here for reaction with an exothermic reaction in the forward direction. And by the way, pressure, hopefully you can see increasing pressure, you're always increasing the yield. Increasing pressure favours the side with least moles of gas. Now, actually, this graph here is for the Haber process. Okay. So yeah, there you go. So I mean, that's like I say, you know, with 2.3, that although the statement's quite small, there is so much there that you have to know or be able to apply. Right, so I hope you found that useful. And yeah, thank you for attending.